So good afternoon. So we will continue our discussion on optimization. So towards the end of the last class I presented some ideas about optimization, the general principles involved in optimization. So we looked at this pictorial depiction of an optimization problem where y is a function of x1 and x2. So if you plot all the constraints, for example if x1 and x2 are the two independent variables, so there is an envelope. Okay, what is contained in this envelope are the various combinations of x1 and x2 which will satisfy all the constraints, but each of these combinations will give a different value of y. Okay, all of which are not equally desirable because the y keeps changing depending upon whether it is a maximization problem or a minimization problem. You want to choose the best value of y which is indicated as an optimal solution. Okay, so there are two cardinal or key points involved in optimization. That is what I have written on the board. The opportunity to optimize stems from the fact that constraints alone do not fix the solution. If the constraints alone are so tight that finally there is an envelope only around that optimum point, then there is only one point, you have to live with it, that is the optimum point, that is the only solution. The feasible solution becomes the optimum point automatically. The meaning of optimum then no longer exists because there is no opportunity for you to find out whether you can improve the value of y if it is a maximization problem or reduce the cost if it is a minimization problem. Therefore the key point is the opportunity to optimize is afforded by the fact that the constraints alone do not fix the solution. The constraints give you enough breathing space, the constraints give you enough freedom to explore the domain. What domain? The feasible domain or the feasible region. Okay. Now where does the smartness lie? Now there are umpty number of possibilities of x1 and x2 which will satisfy all the constraints, but it is not possible for us to explicitly find out the value of y for all values of x1 and x2 because in real life x1 and x2 is only notional. You may have x1 to xn, okay, it is, and each time you have to run a CFD solution or you have to run ANSYS to get the value of y. Y may be stress at a point, the maximum stress in the beam, or y may be the Nusselt number or the maximum temperature in an electronic chassis, the maximum temperature in data center, the supercomputer, whatever. Therefore the smartness lies in not evaluating all the possible combinations of the variables which satisfy all the constraints without going through all the possible combinations, but confidently asserting that this is the optimum. That is where the smartness lies. Is that clear? So these are the two important principles. What is a typical flow chart involved in solving an optimization problem? What will be the first step?
Finding out the objective function. Finding out the objective.
Yeah, even before that. Yeah, that's good. That's an important step. Before that, I'm talking about philosophically and before that. Okay, is there a need? First we have to establish the need for optimization, whether this problem is worth optimizing. Okay, so first we have to establish the need for optimization. Fine. So we have now decided that optimization is required. What is the next step? Yes, no, that's all fine. Then once we want to optimize, then
objective function.
Set up the objective function. Immediately following this, set up constraints. Good, set up constraints. Then then yeah, that will come automatically. Then before solving, no,
Whether there exists an optimization.
that you won't know.
But when constraints are fit, you can find out whether.
No, that is okay. That way m is less than equal to n, where m is the number of constraints, n is the number of variables. All those are. You will set limits on the bounds for the variables, right? Non-negativity constraints, huh?
Come under constraint.
No, but bounds need not be constraints. Bounds are not the. We don't have to state everything as a constraint. Okay, if you want, you can take it as a subset, but let us explicitly say set limits on variables. Then no, that's LP. I mean, so choose the method, right? Choose the method. Once you choose the method, then there is a decision box. Does the solution satisfy the convergence criteria, right? That is, the change in y with respect to 2 consecutive iterations is less than this, or y new minus y old divided by y new modulus of 100 is less than 0.01, 0.01, whatever. Does what did I say? Does solution, okay. Does optimum satisfy? If it is yes, you stop. If it is no, then you go back. Okay. There could be several types, several variants to this. There could be several types of flow charts, but this is indicative. This gives you a broad idea of how we go about solving an optimization problem. All right. Now,
if it's the condition is no, why are you going to set limits on variable? You should choose another method.
not set limits. Sometimes there are some physical limits. We don't want to pressure. Suppose you want to optimize a power plant. Pressure, we want to set limits. Pressure is less than 160 bar. Temperature less than 560 degrees centigrade, which the objective function will not know. These are coming outside. These are coming from outside. I mean metallurgical restrictions. Okay.
Why are we coming back to that and not the choose the method?
Oh, that is your question. No. What happens? Sometimes we are. I mean, my response to your question was with regard to issues like maximum temperature in a power plant or the admission pressure for steam and so on. In this case, what happens is sometimes we don't want the solution to go out of this thing. Sometimes extraneously the analyst may put some tight conditions on the variables. So you relax this or you tighten that. So I am not saying you should cheat in such a way that you say if x is 5, you say x is not less than equal to 4, x is not greater than equal to 6 and get 5. I am not saying like that, but sometimes it to make it more convincing, we do not want a helter-skelter search in the domain, right. Sometimes you intelligently suppose you are searching for, you want to determine thermal conductivity of some substance, a metal. You do not want an optimization go from K is equal to 0 watts per meter per Kelvin to infinity, right, 0 to 1. I know it is a metal, so let me say it will vary from 20 to 400 or something like that. It is okay for me to do that. As an engineer, as a mathematician, I may not want to do that. Any variable can go between 0 to infinity, but as an engineer, I know the bounds for viscosity, specific heat, density and so on. So I will apply realistic bounds. Is it okay? Fine. Now, if you do not like it, you can absorb this in the constraints and then it has to come here, right. Fine. This is a general flow chart for solving an optimization problem. Now what could be a very desi or a, I am not denigrating the word desi, but what, so we are live, no. What could be a naive or what could be a crude optimization method? Substitution what man, there will be hundreds of values. So let us talk about a, so now we got an idea of pictorial description of a optimization problem. Y is a function of x1 x2, where does the opportunity to optimize arise, where does the smartness lie, how do you go about solving, then this recipe you can apply by, so if you know various techniques for various kinds of problem, you will decide which is the most appropriate technique and solve. Now even before starting all this, just like you did the pump and piping problem, I mean we did not go through all this, you adopted some crude method, maybe you plotted, it was just one variable you plotted, or you wrote a program and make small increments in the variable and try to find out where it hits some maximum or minimum. So what could be a so what could be a helter-skelter approach to optimization?
Choose one point
Okay.
and then find out
Value of y.
value of y.
Good.
And then find out value of y at 4 points.
Okay.
And then whichever direction it is increasing.
Very good. That is one. That is what he says is a two-dimensional problem. Choose one value of x1, x2. Find the value of y. Choose east, west, north, south. Find in which way it is moving. Then move in that direction. Then again choose. This is actually called This is actually called this is one kind of search which I will teach. Which I will teach. This is called the lattice search. Okay. This is called the lattice search. We will come to it little later. The helter-skelter approach will be choose even before that the crudest of them all will be choose some combinations of variables get y, find the highest or lowest and declare that that is the optimum. Okay, get y, very dangerous, but it is better than not doing anything at all. You are not finally getting the global optimum is not guaranteed. So this is basically a non-serious approach to optimization, but there may be some limitations. It is so the practicing engineer will say that it is not possible to get all combinations of variables. There are only a handful of combinations. These are the combinations which I can manufacture, because from a machinability point or manufacturability point, or when I am outsourcing some components, these are the values of x1, x2, x3. If I work out the value of y for these combinations, it is enough. So we are not talking about optimization where these techniques will work. We are talking about real serious optimization where there are many variables, and then the constraints give you the freedom to search the optimum, search the feasible domain and so on. Okay. So there could be some crude approach where you will get some idea, so you will get which is a better solution compared to the other, that is all, but global optimum is not guaranteed. Therefore first the next half of the course we are going to do all this only after we are convinced that there is a need for optimization, and methods like this will not work. If either because of cost, money, if either because of money and effort you do not want optimization, you do not need optimization, or your problem is such that some engineer, some manager, some person working in the industry will tell you no, if these 10 or 20 combinations are enough, then we have to just close shop and go home. But we are talking about the serious optimization in thermal sciences and this thing where there are plenty of variables, like you want to minimize the payload, you want to minimize the weight of the aircraft or spacecraft, you want to minimize the weight of the Boeing 787, you want to increase the bhp per ton of a racing car, or you want to increase the fuel efficiency and all this, where you cannot simply put 4 or 5 designs and you want to have a CAD design, then you do a finite element analysis, then you go through the thermodynamic analysis, you want to do all this. When you are doing all this where these techniques will not work, then it is time to understand serious optimization. That is what we are going to do the next 7 or 8 weeks. Alright. Now let us start. What are the various optimization techniques which are available? Sometimes when you are in the business of doing research, when you write some papers, when you write a serious paper on optimization, I have seen comments like this: why do the authors struggle so much? Let them take some 10 possible combinations of variables and find out the value of y will. So I would write 2 pages, whatever I told now I would write, and then say that it is not possible and this thing, and sometimes this common sense will fail. So how do you arbitrarily choose these 10 combinations and all this? Okay, so it will not work for all, otherwise the whole field would not have developed. Okay. Now optimization methods. There are several ways of classifying this. Some people classify the methods, some people classify the problems. So we will combine both. Optimization methods are broadly classified into calculus and non-calculus, calculus methods and search methods. What do we do in a calculus method? Use derivatives. Use derivative to determine optimum, correct? Okay. Here you use objective function information. Like what Abhishek said, you start with the point, take east, west, north, south, get the new value. But in a calculus technique, we completely forget about that. We just take dou y by dou x and find out what are the values of the x1, x2, x3 at which y becomes an extremum. We do not even care about the value of the optimum. The value of the optimum is the value of the function y at the optimum is a post process quantity in a calculus method. It is incidental. You will find out what are the values of the design variables at which the solution becomes stationary, or dy by dx becomes stationary. Okay. So the calculation of the objective function is pushed to the end in the calculus technique, but in the search method it is the objective function, always you are comparing y1 with y2, y3, y4, find out which is the maximum and then perturb that, and that is, so that is the basic difference between these two methods. Okay. Having said that, calculus, but what is the important requirement? First, objective constraints must be differentiable, constraints must be equalities, right? Otherwise if it is an inequality we are going to have trouble. Okay, slack variable, other things, but it is more difficult. Constraints must be equalities. Of course this is debatable, right, but generally constraints must be equalities, and constraints must be differentiable. Why only constraints? Objective function, right? There is no requirement. There is no requirement in so far as search methods are concerned, right? In each of this you can have single variable, multiple variable. In each of these you can have What are C and U? Constrained and unconstrained. Okay, so you can have C constrained please note that this division basically represents two types of methods. From here on I am classifying the problems. Now I have indicated both the type of optimization problems you will normally encounter and the types of methods used for solving this. So you can have a multivariable unconstrained optimization problem which can be solved by a search method or a calculus method, okay, or you can have a single variable constrained optimization problem which you can solve by this or this. So you can have you can put actually x1 and x2 for example, or x1 is the type of optimization problem and x2 is a type of optimization method, then you go and choose whatever is most appropriate to you, alright. So without much ado we will start off with the first technique, the Lagrangian multipliers. This is a duster. One of the most powerful optimization techniques that is calculus based, okay, calculus based. So let us write some stories about this calculus based. Unconstrained and constrained problems. I wanted to say something else, unconstrained multiple variables. Oh, is it like this swine flu vaccine? So it is a cure all, everything is there, unconstrained, constrained, multiple variables. So that is it, you just learn Lagrange multipliers and go home. What is the catch? The constraints must be equalities. Okay. Number of constraints must be less than or equal to the number of variables. Constraints must be equalities. Okay. Objective function constraint must be differentiable. These restrictions notwithstanding, there is a wide class of problems which fall under the category which can be eminently solved using the Lagrange multiplier method. Okay. So what is this method? So consider the general optimization problem. Optimize y is y of subject to I am putting this as 3, it is not correct. This is some m plus 1 or something, it will confuse us. So I am just putting it as 3. Okay. So the funda is m is less than or equal to n, correct. If m is equal to n, the constraints themselves will fix the solution, that is the optimum solution. If m is less than n, there will be a feasible domain where you can possibly explore. If m is greater than n, it is a over constraint optimization problem. Alright. So, what does the Lagrangian multiplier now say? The Lagrangian multiplier method says that the solution to this optimization problem of a m constraint n variable optimization problem with m equality constraints and n variables is akin to solving a set of equations which are generated like this. So, the Lagrangian multiplier suppose you have okay. So, lambda is a scalar, its lambda is lambdas. What does it mean delta y minus lambda delta phi equal to 0? What does it actually mean? It actually means lambda 1, can I write for the first one, dou phi 1, tell me, dou phi 1 minus not dou, everything is dou x1, right, correct, is equal to 0. How many equations are there? How many such equations are there? N. Good, n equations. Apart from this, so these are n scalar equations. Apart from this, what are the other equations you have? You have m constraint equations. Okay, phi 1 equal to 0. Number of variables, the total number of equations is m plus n, total number of variables is m plus n. So, if these m plus n equations can be simultaneously solved, you will get the values of x1, x2 up to xn at which y becomes stationary. Apart from that, you get an added bonus lambda 1 to lambda m. These lambdas are called the Lagrangian multipliers, Lagrange multipliers. It is too premature at this stage to discuss what lambdas are. I will give you a physical feel for lambda after we work out a problem and you get an intuitive feel for what lambda is, and then I will turn back and say what is the interpretation, what is interpretation we have for lambda. Fine, right. So, this is the procedure for solving the Lagrange multiplier method. Now, it may look nebulous, cloudy, vague and all that. Once you solve problems, it becomes easy, right. So, we can extend it for the unconstrained problem also. Let us extend it to the unconstrained problem, which makes life a lot easier. This comes from vector calculus. I will also prove this in one of the later classes. what is the proof of the Lagrange multiplier method, what is the graphical interpretation of the Lagrange multiplier method, what is the physical significance or the economic significance of lambdas and so on. Vinay, you have a problem? Okay. So I expected a question here. I expected a question at least from one of you.
How does that equation mean that we are solving for the output?
No, all that I am going to explain. Why not substitute the m constraints into the objective function and reduce the order of the objective function? That is a question I expected. Are you getting the point? You can substitute the constraints and reduce the order of the equation. You can substitute these m for these m constraints into the objective function and reduce. So, but this is not always possible because sometimes the constraints are too difficult to mess around with. I mean, they are very complicated and it's very difficult to do so, right? Otherwise, conceptually and mathematically, it's perfectly legal for you to substitute. Okay, for example, if you are finally n minus m is equal to 1, if you substitute m constraints into n, finally you will be left with only one variable you can solve. Okay, just like our substitution in your solution of simultaneous equations and so on, right? Unconstrained optimization problem. There are no fees. Therefore, Lagrange multiplier reduces to very simple. So, I think you want to give some numbers for this. So, I will just call this 5. Okay, Lagrange multiplier. So, it is very simple. So, this just reduces to so, if it is just a one variable problem, it could be like this, it could be like this, or it could be like this. A, B and C, right, y versus x. So, A is the maximum, B is the minimum and C is the inflection point, where unfortunately the second derivative is also 0. So, the Lagrange multiplier method will give you only the values for the independent variables at which the function becomes stationary. It helps you to locate the extremum. However, second order necessary and sufficient conditions are required to determine whether it is the optimum is a maxima or a minima or an optimum or an inflection point. I come again, we are working only with first order conditions, we are making the first derivative stationary, therefore it will not tell you whether it is maximum, minimum or an inflection point. So, higher order necessary and sufficient conditions are required for doing this. However, in many engineering problems it is possible for you, once you have made something stationary, it is possible for you to figure out. You are working so much, you have done a complete analysis of the IC engine, you did simulating this thing, you struggled in MATLAB and finally you optimized. You will not get a solution where the specific wheel consumption is the maximum, right? When it becomes when you hit an extremum, it should be SFC is minimum, right? It is very unlikely that after all this hard work you will end up with a solution where SFC is maximum, right?
Second order differential equation when there are number of variables is difficult.
Second order differential.
Yes, sir, if you differentiate, when you find out the second order equation,
Ah,
when there are number of variables,
yeah,
how can we come to a judgment whether it is reaching?
no
a
problem. You have to
maximum?
evaluate what is called the Hessian matrix. I will teach you. So, the Hessian matrix must be positive definite. Is it going above your head? Don't worry. So, there is something called the Hessian matrix. Okay. So, you can look at the, don't worry, it is not for a 2 variable problem, it is pretty straightforward. You will get the determinant. Okay, this is called the Hessian matrix. You look at the determinant of this and see whether it is positive definite, whether the leading diagonal this is positive and the whole thing is determinant is positive negative. We will do all this later on. Huh? Okay, so problem number 21. Get the minimum of the following function using Lagrange multipliers. Yeah, first decide whether it is single variable, multiple variable, constrained, unconstrained. Go ahead, shoot, 5 minutes. What is the equation of a? Equation of a circle. The equation of a circle. Get the minimum of the following using Lagrange multiplier: x1 minus 8 whole square plus x2 minus 6 whole square. 0. When does it become stationary? 8 and 6. So it's a pretty straightforward, man. Huh? And you thought Lagrange multiplier is very difficult. Yeah, finish it. Do the dou y by dou x1 equal to 0, dou y by dou x1 equal to 0, get the value of x1, x2 optimum, substitute, get the value of y. If you want, go ahead and take the second derivatives. No, I have not taught you Hessian and all that, forget about it. Okay, so dou y by so I denote the optimum by plus, you can use star or whatever, opt, subscript or whatever, to distinguish it from general x1 and x2. Okay. What is the solution? So y1, y2, y3, y4 and all that, right? This is y equal to 0. Okay. What are the circles?
Contours.
What?
Y equal to constant.
Yeah, give a name. Give a name. Iso-objective contours. Okay. Any point on that as the same objective function. Iso-objective contours. Lines joining points having equal rainfall. It's called. Huh? ISO? Yeah, people who have taken atmospheric science courses. They call ISO Hayats, right? Isobars, isocore, isotherm, isoentropy, right? Isoefficiency, isocost, iso-CGPA, whatever, iso-CGPA contours. Okay. So this is a simple unconstrained optimization problem, but I will give a little more, I will give a little twist to it and give a slightly more involved unconstrained optimization problem before we break, and then we come and take more serious problems. We will start looking at some heat transfer problems and use Lagrange multiplier method. This Lagrange multiplier method is important, it will go on for 4-5 classes, right. So surely there is one question in second quiz on Lagrange multiplier, second quiz NSEM, and one of the most important topics in optimization. Okay. So two variable problem. So if this is x1, x2, it is y, optimum, a depiction, I just say a depiction. Generally you can indicate like that. Okay. Maximize of course needless to say using the Lagrange multiplier method. Is it constrained or unconstrained? Don't worry about x1, x2, x3. Is it constrained or unconstrained? It is an unconstrained optimization problem. I am giving x1, x2, x3 greater than 0 because this fellow can give, you can put minus values and say that some x1, x2, x3 are physical variables. You cannot produce minus 4 tables and minus 6 chairs. Maximization of a plus y is equal to a plus maximization of y, correct. Therefore minimization of a minus y is equal to a minus minimum of, I mean you can use that.